Next, we will do a root level network analysis. And for this, we are setting up some configuration. Rest of everything is self-explanatory, but we are restricting to minimum trip per route to be 5. And we are expecting that the default server should be 2. Now, what does this default server, what does this MMC mean? We will discuss at length in a greater detail, but for now, since we are assuming that at each destination or at each source there is one server serving all the trucks, right? So this is in a way doing a simulation by assuming that if there were more than one truck, in our case we have assumed it to be two. Sorry, if there was more than one server, right? What will be the impact on that route? Is it going to be less congested? Is the utilization going to be better? It is going to be better served? For sure it will, but what is going to be the impact? So okay, now let's run these cells. And for the pre-processing, we are again starting off with those four basic variable. On top of that, we are creating creation hour and start hour. It is required for doing the arrival rate calculation and service rate calculation. We are also calculating route complexity on the basis of actual time divided by segment actual time. And why we are doing this calculation is if the root complexity is greater than 1.5, so we will be bucketing it into multi-leg or into single leg. And why a trip would have a root complexity 1.5 is because, let's say, if a truck was carrying an item of the same segment, like consider stationery and consider pencil, maybe like a truck was carrying item of pencil and we have the segment actual time to deliver all the pencils, so it is going to come exactly to one or kind of very similar to the segment actual time. So those analysis will be done under single leg analysis. But in case if the truck is carrying multiple stationary item, right? So obviously it is going to be more than the segment actual time because there are multiple segments here, and hence it will come into multi-leg category, and that analysis will be slightly different. And obviously we would expect more delays or more scope for process improvement in multi-leg as compared to single leg, right? Okay. Next, we are looking at the batch density. So to calculate the batch density, first we are calculating the root R density. So for each root, right? So for each root ID and a given creation R, we are grouping by these two, and so we will arrive at the root density. So this is how it would look like, that for each given route and for each creation hour, what is the route batch density? Like how many, what is the queue size? How many trucks are there in the queue, right? And then we are trying to calculate the average route density, that even for, like, so for each route, right, we will have 24 hours in a day, and taking the average of all that, we will arrive at average route batch density. Now what is this enabling us to do is, this is kind of giving us a rough estimate that on each route and for a given hour of the day we would have two trucks or two full trucks being transported, this kind of information. And from here as well, like if I do a max or a min, I would get to know that which route has the maximum uh, congestion. Let me just, like, do it now itself. So instead of head, if I paste this and say max, let's see if that Which route? Which route has the maximum congestion? So, for this route ID, for a given day and given hour of the day, we can expect 100 trucks to be getting transported there. So, level one business analysis we can draw from here itself that maybe try to make this route less congested. Okay. Now let's look at what all are the helper function we would be needing to carry on the uh, uh, Erlang C analysis or MMC analysis. Let's first understand the meaning of each. Lambda, everywhere you see lambda, that is the arrival rate, and mu, which is the service rate per server. C is the number of parallel servers, and rho is the utilization. Now that we know the meaning of all these variables, let's try to see how we can use the MM1Q or MMCQ analysis to find out the congestion and expected times. For both these analysis, the process remains the same, which is the 6 steps mentioned here. First, we calculate the offered load, which is given by the ratio of lambda is to mu. Then we calculate the utilization per server, which is given by lambda over C into mu. Then we calculate the probability of waiting, PW. Then we move on to expected time in the queue, which is given by PW over C mu minus lambda. Then we move to expected time in the system, which is the WQ, which we calculated in the previous step, plus 1 over mu, which is basically WQ is the waiting time plus 1 over mu is the average service time. And then lastly, we will calculate the average number of customer, which is given by L into WQ. And few of the sanity check that we can do is the row should be less than 1. It basically means that if the arrival rate is greater than total service rate, the queue goes faster forever. So we will not be able to service that queue. And another thing should be that as row reaches 1, wait time and queue length approaches infinity, and hence it leads to systems congestion. Another thing is lower both waiting probability and waiting time if we have a row which is greater than 1, and at one point adding servers will not reduce any of the congestion. So hence we will try, or the business should try from their end to keep the row less than 1. Okay. And these are the helper function which will help us calculate it, the rank C or the MMC. So in this we will calculate the waiting time, and uh, sorry, in this we'll calculate the probability of to wait, and here we'll calculate the waiting time. And let's now look at how we are able to arrive at each of these lambda, mu, rho, w. Arrival rate is calculated by taking the creation hour and on the granularity of route schedule UID, and and first arrival is going to be the min and last arrival is going to be the max. Once we have our data grouped on a level of route schedule ID, we can go on to calculate the rate. And how we are going to do that is first we would take the difference. Basically, we are finding the time delta between the arrival and the first arrival. And once we have the delta, we'll store it into active hours per arrival. And the rate would be calculated by taking each arrival and divide it by active hour of that arrival. Same calculation we'll do for departure. And in as I talked up before, that in beginning of analysis we set some configuration, and then now here we will be acting on those configuration, that the minimum, basically what we are trying to do over here is we are counting the trip number of trip in a given route, and then on we we are merging it on the counts, and we are trying to compare if these counts are greater than the minimum number of trip per count for our analysis. And as I discussed before, we have set it to 5. So this is filtering for all. Basically, this will filter the routes where we have it set to 5. Then for the MM1 analysis, what all we need is the MM1 row, which will be calculated by taking the arrival rate and the service rate, and we will again be eliminating all those routes which has this row greater than 1, because as we now discussed that that leads to um, exploding of the queue, and we are not interested in those situation. And similarly for mm1, for mmc, we will just set the value of c according to our number of servers that we had configured before, default servers, which is set it equal to 2. So that's what we are doing it. We are configuring it to our default server, and the formula for both of them is going to be the same. So after we have done this processing, let's try to look at how the data is now looking. So, so for a given route, this is the number of traffic on the route. This is the first arrival. This is the last of arrival, and this is active hours per arrival, and this is lambda, basically the arrival rate. Mu is the servicing rate, and trip count is again like the traffic congestion on that route. Rho is the ratio of lambda by mu. L is the number of truck waiting to be processed. W hours is the processing expected processing time in hours for the entire 65 trucks. Same thing when we convert into a minute. And these are related to the MMC calculation, where we have increased the number of server from 1 to 2. So hence you immediately see that the arrival rate has reduced. The WQ, which is the expected processing time, this is also reduced. Minutes, for like the overall minutes also, like it has drastically reduced from this to this number. Okay, let's move on to our, so from this analysis we would be able to first of all, like, forget about the C part. Like this is a simulation that if our stakeholder wants us to perform, we'll do it. But from this overall we can see that on which route we experience the most congestion, which route is having like the row greater than 1, which we already eliminated. um, which route has the most poor servicing rate, and which route has the maximum expected arrivals, and which route has the maximum wait time, which is the total of arrival time plus the processing time. on that route. So from here also we can diagnose a lot of issues in our system. But now let's look at delay amplification. Earlier we saw the same delay amplification from a trip point of view. Now multiple trip would be happening on a single route. Now let's try to look at the same analysis from a route point of view. And again, over here, we would have the delay amplification factor. So from this factor, we would be able to identify that on which route we are experiencing the greatest bottleneck. Uh, and finally, we will roll it up in a single line item uh, for us to like visually try to see that which are the least performing trip, I mean, the route and what treatments we can give for each route. So over here, you see that we have incorporated all of our calculated field in our existing data. So up till this column, we had our data. And let's say if someone is interested in doing this kind of analysis that they want to see carting versus full truckload, they can go with this analysis as well. And now let's try to visually diagnose the issue, starting first with uh, the top delay amplifying routes. The reason why they have not given us the exact route is because this is also a business secret that they don't want to reveal. Obviously, they would have invested a lot of time in identifying the most optimal route. So they have like uh, coded it into these IDs. But for sure, this route needs a better optimization because if I compare it with these are the top 10 routes which are having uh, like abnormal delays in it. And you see that this particular route, even when we compare it to the outlier situation, has twice the number of delays in it. For sure, they got to like optimize these. And let's and then these are the routes where we have utilization close to 100%. Now we just saw what is the effect of a route reaching a utilization close to 1 or 100%. It results in exploding queues, and no matter how many servers we employ there, we would not be able to like fulfill the order. So at first priority, these routes should be uh, considered and analyzed and diagnosed in such a way that their utilization, if not reduce it to 60%, so at least try to bring it down to 80%, so that the orders are getting fulfilled on time. And ultimately, the user satisfaction is directly proportional to the order fulfilled. So, hence, for better user satisfaction as well. And these are the wait time. So I think even the amplification and wait time is trying to give us the same information. Amplification is normalized by the nature of its formula. Let me also show you the formula for amplification. It is normalized by the mean of the distance, but total time or the wait time is not normalized. Basically, this is the sum total of the time in minutes that the truck has to wait. So again, pointing out to the same conclusion that these routes should be analyzed further and should be given some treatment to reduce their wait times so that the customers are well satisfied and even the people who are working there do not have to work overtime to fulfill the orders, because all almost all of these routes are reaching to 100% of their utilization. So it is inevitable that there would be a situation of exploding queues. So, which is not good for any of us, but generally the people who are most affected is the people who are actually working there. So this was it about the root analysis. I will see you guys in the next video, and there we will be looking at some of the ML related analysis or the predictive analysis that we can perform on this data. Thanks.